हाँ हाँ Yes, a very good afternoon to all. Yes, hello everyone. A very good afternoon to you all. So let's begin with a new chapter. And the name of the chapter is Refraction of Light, chapter number 6, Refraction of Light. So before starting with refraction of light, now the first thing that which we all should know, the difference between refraction and reflection. Correct? Now this reflection is a different term and refraction is a different term. So for example, if I talk about reflection, so what is exactly reflection? I will give you one example. Let's consider that I am in a particular room, fine? So if I take a ball and if I will hit it against any of the wall, what will happen? It will come back to me. It will bounce back to me. That means reflection means anything is thrown at some of the place, it will come back to you. Okay, but for refraction, it is something different. So let's understand what exactly is refraction of light. We are understanding
Chapter 6
in the terms of light.
Refraction of Light. Students, in this chapter, we shall learn some important topics like refraction of light, laws of refraction, refractive index, dispersion of light.
Fine. So this four topics is extremely important. Like see, it is refraction of light. We will understand what exactly refraction means. Like see, reflection now everybody knows it. Like see, many of you have given me the answers. Shraddha has given me the right answer. Then Satish has given the right answer. Very good. It reflects back. But when it comes to refraction, what exactly is this word refraction? We will learn this in this chapter. Also, we are going to read about the laws of refraction. What exactly are the laws of refraction? After that, we will study about the refractive index and then the dispersion of light. Now, what is the meaning of the word dispersion and how the light can be dispersed? We will study each and everything in detail in this topic. Let's see the next one. See.
Refraction of light. Try this. Material, glass, 5 rupee coin, pencil, metallic
Hello
vessel,
Mayuri.
etc. Activity 1. 1. Take a transparent glass and fill it with water. 2. Dip some portion of a pencil vertically in water and observe the thickness of the portion of the pencil in water.
See.
3. Now,
See. Here as we can see that they have immersed a pencil inside the water. Can you see the thickness? Can you see the difference between the thickness? Is this the two different pencil? No, this is the same pencil, but the thickness when it is outside the water it is different, and when it is immersed in the water it is also different. Okay, now let's see the third part.
keep the pencil inclined to water surface and observe its thickness. In both cases, the portion of the pencil inside water
Is the
appears to be
thicker.
thicker.
So do you all agree that yes, that the pencil when it is outside the water and when it is inside the water, both the portion is different. Like see, above it was thinner and now it is thicker.
Than the portion above water. In the second case, the pencil appears to be broken near the surface of water.
Yes, this is
Why does
something
this
very
happen?
interesting thing that see this is the same pencil but when it is outside the glass, yes it is different, and when it is inside it appears to be broken. It appears to be slightly shifted. Now what exactly is the reason behind this? Let's see.
Activity 2. 1. Keep a 5 rupee coin in a metallic vessel. 2. Slowly go away from the vessel. 3. Stop at the place where the coin disappears. 4. Keep looking in the direction of the coin. 5. Ask a friend to slowly fill water in the vessel. You will be able to see the coin once the level of water reaches a certain height. Why does it happen? In both the above activities, the observed effects are created due to the change in the direction of light while coming out of water. Light changes its direction when going from one transparent medium to another transparent medium.
Now this point is extremely important. See what is written? Light changes its direction when going from one transparent medium to other transparent medium. This is called as refraction of light. Now here we will understand what is refraction of light. See, as I have told you earlier, when I say reflection of light, that means if I am using a torch and if I will allow the light of torch to fall on any one of the surface, it will bounce back to me. It will come back to me. That is called as a reflection. It is reflecting back on me. But in refraction, the light will not come back. The light will not bounce back. Rather, it will change its direction. See, if I draw a line, if I draw an imaginary line, see, try to imagine a line in a straight way. In a straight way, it moves like this. But see, when it was in the air, it has some different direction. And when it is moving from the air to the water, it has changed its direction. So yes, my students, refraction of light is the light changes its direction. See, the light had changed its direction. But when is it changing the direction? When it is moving from one transparent medium to another. Now you just can't say from one medium to another. It should be transparent, like air, water, glass. Now all these things are transparent. We can see the changing of the light is visible. Okay, so light changes the direction. So as you can see, the light has changed the direction. Can you see a slight bend over here? Yes, this light is changing its direction when moving from one transparent medium, which is air, to the other transparent medium, that is water. So light changes its medium when moving from one transparent medium to the other. So this is called as the refraction of light.
This is called the refraction of light.
Correct, Shraddha, correct. So when it changes, it is called as the refraction of light. Now pay attention to this.
Activity 3. 1. Keep a glass slab on a blank paper and draw its outline PQRS as shown in figure 6.1.
We have kept a glass slab over here and we have just traced out the border and we have labeled it as SRQP. Okay? Or as PQRS. Anyway, in the clockwise direction or the anti-clockwise direction, we can say it. Now see what next
2.
we have to do.
Draw an inclined straight line on the side of PQ so that it intersects PQ at N. Pierce 2 pins vertically at 2 points A and B along the line. 3. Look.
See. You have to just do that, and now from this side you have to look it from the other side and you have
Look
to
at the
pierce
pins
the pin.
A and B from the opposite side of the slab and pierce pins.
See, can you see A and B in one line? Yes, now you have to maintain this line and you have to pierce the pin C and D in the opposite direction. See, pay attention.
C and D vertically so that the images of A and B.
See, you have to pierce the pin P and C in such a way that this A and B in the opposite side of the slab and C and D to the opposite end of the slab all should look in the same line. See, you don't have to look it from the top view. You have to look it through the glass. See, after looking it through the glass, you can see A, B, C, D all are in the straight line. They should maintain a line. Okay?
Are in line with C and D. 4. Now remove the chip and the pins and draw a straight line going through points C and D.
See, so when you are looking it through the slab, you can see it that A, B, C, D are in the straight line. But as soon as you move from the side angle to the top view, and when you remove the slab, you can notice that A and B are in the different direction and C and D are slightly moved. Now why is this? Because when the light is traveling from one medium to the other medium, it is changing its direction, and also when the light is coming from one medium to the other medium, it is again changing the direction. So basically this is called as refraction of light. So again I repeat, the light changes its direction when moving from one medium, from one transparent medium to the other transparent medium. So this change is called as the refraction of light.
5. Join points M and
Correct,
N.
Shraddha.
Observe the incident ray AN and emergent ray MD.
See, now this is called as the incident ray because we will also see this.
The first refraction occurs when light ray enters the glass from air at N on the side PQ. The second refraction occurs when light enters air through glass at point M on the side SR.
Okay, so the second refraction, see how many times the refraction is taking place. I just know one thing, that when the light is traveling from one medium to other medium, one refraction will take place. Now for example, if I consider the example of this thing which has been displayed on the screen, now see from where the light is moving to where? The light is moving from the glass to the slab. Again I repeat, from the air to the glass. Now this air is a transparent medium, so light is moving from one transparent medium to the other transparent medium, that is glass. So when the air is moving from glass to glass, it is refracting. In simple terms, it is changing its direction. So one time the refraction took place. Now the light is moving inside the glass, and again the light has to come from glass to again back to air. So by now this light is again coming from one transparent medium glass to other transparent medium air. So here second refraction took place. So first refraction took place here and the second refraction took place here. So two times the refraction is taking place at N and at M. Okay? Pay attention.
For the first refraction, the angle of incidence is I, while for the second it is I1. The angle of refraction at N is R. Note that I1 is equal to R. In the second refraction, the angle of refraction is E, which is equal to I.
Now pay attention. See, now as this light, the beginning, the first light, this light is incidenting, as this light is going inside, as this light is first, it is incidented. It is called as the angle of incidence. So we have written it as angle I. And as this light is refracting in the opposite transparent medium, we have written it as R. Okay, so see here I1 and R, and this is traveling throughout the glass, and again it has emerged out. This light has emerged out, so we are writing it E. Now pay attention. See, this incident light I and this emerged angle E, this incident angle I and this emerged angle E, both are equal, which means if the incident angle is 40, also this angle will be 40 degree. If this is 60, this would be 60 degree. So whichever thing is in air and air, see this angle I is formed in air, this angle I is formed in air. So these two are equal. Okay, and if I talk about the angle formed inside the glass, the refracted angle and the second incident angle, so it is written as I1. Okay, these two are of same measure. So if this is 15, this will also be 15 degree. If this is 20 degree, this will be also 20 degree. Okay, understood?
On both parallel sides, PQ and RS of the glass slab, the change in direction of light ray is equal but in opposite directions. Thus, the light ray MD emerging from the glass slab is parallel to the incident ray AN on the side PQ of the slab.
Okay, so as you can see this, pay attention to this. Can you see the lines are parallel? Can you see this
Ray
parallel lines? See, as they are forming the same angle, definitely as they are forming the same angle, if you extend the line on both the side, you can find that this incident angle and this incident ray and this emerged ray both are parallel to each other. This incident ray is in the air medium and this emerged ray is also in the air medium. So if you extend this line, you will see that both are parallel. Both are parallel. See, because both the angles are equal. Very good. Very good.
AN
Now,
on the side PQ of the slab. But the emergent ray is somewhat displaced with respect to the incident ray.
okay. Now let's see this laws of refraction. Now this is an extremely
refraction.
important topic. Laws
Let
of
us
refraction.
study the light ray entering a glass slab from air. Here, AN is the incident ray and NB is the refracted ray.
Now, before understanding or before moving on directly to the topic of laws of refraction, first we will understand what is incident ray, what is an incident angle, what is refracted ray, and what is the refraction angle. See, if I look at this, see incident ray, the first light which comes and hits is called as the incident ray. So this is called as the incident ray. Now, angle formed by incident ray is called as the incident angle. The ray is called as the incident ray and the angle with respect to the incident ray is called as the incident angle. So it is denoted by I. Now, when it is moving from the one transparent medium to the other transparent medium, to be more specified, when it is moving from the one transparent medium air to the other transparent medium glass, it is called as a refracted ray, not reflected. See, if I would have drawn a line here, this is called as a reflected, but this one is the refracted. It is moving from one transparent medium to the other transparent medium. Okay, so now angle formed with respect to incident ray is called as the incident angle and the angle formed with respect to the reflected ray is called as the reflected angle. Now see what is written. Incident ray and the refracted ray at a point of incident N are on the opposite side of the normal to the surface of the slab of that point. See, this is the normal. The line drawn here is the normal. Now incident ray is on the left hand side and the refracted ray is on the right hand side. So this ray and this ray are to the opposite side of each other. The incident ray and the refracted ray both are on the opposite sides of the normal. This red line which is normal. See, N is the normal. So see, first law, everybody pay attention to the first law. Incident ray, this ray, and the refracted ray, this ray, both at the point of incidence N and are on the opposite side of the normal, at the opposite side of this red line which is normal. Everybody understood this? So incident ray and refracted ray are to the opposite side of the normal. This is the first law of refraction. I hope everybody understood.
Ray at the point of incidence N are on the opposite sides of the normal to the surface of the slab at that point. That is CD.
See, they are on the opposite side of the normal CD. Okay. And the three, incident ray, refracted ray and normal, all the three are in the same plane. All the three are in the same plane. See, and means this is the second part. Three, all the three, this incident ray, this refracted ray and this normal are in the same plane. Please pay attention.
And the three, incident ray, refracted ray and the normal are in the same plane.
See.
2. For a given pair of media, here air and glass, the ratio of sin I to sin R is a constant.
Fine. Now this is the second law of refraction. Now see, as I can see here, this is the normal atmosphere, this is the air. So this medium, this is the first transparent medium is air, and the second transparent medium is glass. So when I talk about air and glass, so for the given pair of media, so in this example it is air and glass, it is written as air and glass. So the ratio of incident to the ratio of the refracted. So again I repeat, the ratio of the incident to ratio of refracted. Now they have not just written the angle incidence and angle refracted. They are writing sine I means this incident ray, and sine R means the refracted ray. So sine R upon sine R, or else you can say the ratio of sine I upon sine R is constant. So second law, that the ratio of the sine I upon sine R is equals to constant. Okay, understood? See, please pay attention.
Here, I is the angle of incidence and R is the angle of refraction. Sine I upon sine R is equal to constant, which equals N.
Yes, now pay attention to this. This is called as the Snell's law. Fine. So now as we have studied the thing in the previous thing, that sine I upon sine R is equals to constant. We have studied this thing a minute before. Now they are considering a constant equals to n. Now pay attention. The ratio of the sine I upon sine R equals to constant equals to n.
N is called the refractive index of the second medium with respect to the first medium.
Now pay attention to this. Now what is this n, which is also called as neta? What is this n? N is the refractive index. As we are studying about refraction and everything, this is the refractive index. But a refractive index of the second medium with respect to the first medium. See, n is called the refractive index of the second medium to the first medium. The second medium here is the glass and the first medium here is the air. So this is the refractive index of glass with respect to air. Now pay attention.
The second law is also called Snell's law.
Yes, this is also called as the Snell's law. So sine I upon sine R is equals to constant is equals to n, and what does this n mean? N means the refractive index, of the second medium with respect to the first medium. This whole thing is also called as the Snell's law.
A ray incident along the normal, I is equal to 0, goes forward in the same direction, R is equal to 0.
Yes, as in the previous thing we were studying that the light from somewhere from air is coming to the glass, and it is in the inclined position and it was making some degree, with respect to the normal. It was making some angle, it was forming an angle with respect to the normal. But here they are saying that in case that the incident ray is making a 0-degree angle, if the incident ray is making a 0-degree angle, so what if the incident ray is 0, obviously the reflected ray will also be 0. That means if the incident ray is coming to the glass slab, it will go out of the glass slab in the same way. So see what is written. A ray incident along the normal, goes forward in the same direction. That means if the incident ray is 0, then the refracted ray will also be 0. Okay? Yes, it is correct. Yes, sine I upon sine R equals to constant, and that is called as a Snell's law. Also this is correct, that I is equals to 0, that means incident ray is equals to 0, then the refracted ray will also be 0. So an incident ray along the normal goes forward in the same direction. Okay, now pay attention.
Index. The change in the direction of a light ray while entering different media is different.
See, now this is a very important thing to understand. See, now same kind of light. See, this is the incident ray. Here it is going from first medium is air. Here also first medium is air. But the second medium here is glass, and here the second medium is water. Now see, when the incident ray is coming here, it is refracting, it is bending, but it is bending in a different angle. And when it come here, that also this incident ray is being refracted and the bend here is different. So the change in the direction of light ray while entering different medium is different. See, from air to glass, the bend is different. From air to water, the bend is different. So it is different for different medium.
It
Now
is
pay
related to
attention.
the refractive index of the medium. The value of the refractive index is different for different media and also for light of different colors for the same medium. The refractive index of a medium with respect to vacuum is called its absolute refractive index.
Now pay attention. The refractive index of a medium with respect to vacuum. See, with respect to vacuum, on one side if you have vacuum with any of the other medium, so the refractive index of a medium with respect to the vacuum is called as the absolute refractive index. Now this part is extremely important. As we say, refractive index is from second with respect to the first, as we have studied earlier. So yes, the refractive index of a medium, see here it is liquid, of a medium with respect to vacuum, with respect to the first thing vacuum, it is called as the absolute refractive index. See, this is called as the absolute refractive index.
Refractive index depends on the velocity of light in the medium.
Okay, so this refractive index depends upon the velocity of the light in the medium, that what exactly the velocity. See, in the vacuum it is written as V1, and the velocity of the light in the liquid in the next medium it is V2. It is considered as V2. Okay, now let's move on. Now let's move on to the next thing.
Refractive indices of some media.
See, here the absolute, it is given here. So just for the reference purpose, we can see for air it is 1.0003. The refractive index is 1.0003. For ice it is 1.31. For water it is 1.33. Alcohol it is 1.36. Kerosene it is 1.39. Fused quat it is 1.46, and the trumpeton oil it is 1.47. So this is just only for the reference purpose, and whenever if such kind of what I can say sums has been asked, you need to know all the refractive index of the respective things. Okay.
Let the velocity of light in medium 1 be V1 and in medium 2 be V2. The refractive index of the second medium with respect to the first medium, 2n1, is equal to the ratio of the velocity of light in medium 1 to that in medium 2.
Okay. Now pay attention to this. Yes. Now pay attention to this. You should know how to pronounce it and how to say it. Now, refractive index of 2 is to 1. Let's see. We will pay attention again. See what is written.
V2.
The refractive index of in first medium. See, this is the first medium and this is the second medium. For first medium, we have air here, and for second medium, we have glass here. Right? So now let the velocity in the first medium be V1, as it is first medium, we have written as V1. Now as this is the second medium, we will write V2. Okay? So
the refractive index.
The refractive index of the second medium with respect to the first medium, as we have kept on moving on the same thing. The refractive index of the second medium with respect to the first medium.
Index of the second medium with respect to the first medium. 2n1.
See, refractive index. N means refractive index. Refractive index of the second medium to the first medium is equals to the ratio of the velocity of V1 to V2. It is the ratio of the velocity of the light in the air medium to the velocity of the light in glass. So it is written as V1 upon V2. Again I repeat, refractive index of the second medium to the first medium, it is velocity V1, velocity in medium 1 to velocity in medium 2. Okay, fine. This is extremely important. Don't get confused between this 2 and 1 and 2 and 1. It is always written as like this only, refractive index of the second medium to the first medium. But when you write the ratio of the velocities, the first medium velocity should be written upside and the second medium velocity should be written below. Okay? Yes, so this is important to understand.
1 is equal to the ratio of the velocity of light in medium 1 to that in medium 2. Refractive index of second medium with respect to first is equal to velocity of light in medium 1
First medium
v1 upon velocity of light in medium 2 v2.
Okay, now if I talk about similarly, see if I talk about
1 with
refractive index of medium 1 with respect to medium 2. Now see, this has been changed. Now here it was refractive index of the second medium to the first medium. So I have written the velocity of the medium 1 first and then the velocity of the medium 2. But now here if we write refractive index of the first medium with respect to the second medium, then automatically it would be inverse. It would be velocity of the light in medium 2 upon velocity of the light in medium 1. In short, it will be v2 upon v1. So please pay attention.
respect to medium 2 is equal to v2 upon v1. If the first medium is vacuum, then the refractive index of medium 2 is called absolute refractive index and is written as n.
Okay, so see, as I have told you here, it is v2 upon v1. Okay, yes, let's move on to the next thing. Twinkling of the stars. Now this is one of the important topics.
Effect of atmospheric conditions on refraction of light can be seen in the twinkling of the stars.
As we say that in the night, if you have a clear sky, you can easily see the twinkling of the stars. Now what exactly happens, what all things are involved in this, we will study this in this chapter, in this part. Okay.
Stars are self-luminous and can be seen at night in the absence of sunlight.
Now this is the basic thing which we all know, that in the absence of the sunlight, we are able to see the stars. They appear to be a point
sources because of their being at a very large distance from us. As the density of air increases with lowering height above the surface of the earth, the refractive index also increases. Starlight coming towards us travels from rarer medium to denser medium and constantly bends towards the normal. This makes the star appear to be higher in the sky as compared to its actual position.
So yes, see as it is written. So can you see this? Yes, exactly. So as we have a star somewhere in the sky and in the absence of the sunlight, you can easily see the star. But when the light from the star is traveling all the way along from where the star is till the person on this earth, the light has to travel from different medium. So what happens is it gets refracted. So it gets refracted. So there is a small bend of the, what we can say, there is a small bending and finally it reaches to the eye of a human being. Okay, so actually the apparent position of the star is somewhere else and it tends to appear somewhere else. The changing apparent position of the star. So see, pay attention.
The apparent position of the star keeps changing a bit. This is because of the motion of atmospheric air and changing air density and temperature.
See, you can see that when the light is falling in the light is about to fall in the eye, it is changing the apparent position. Sometime it is looking at the right hand side, the left hand side. So this changing appearance of the position it appears to be blinking, so it keeps on blinking. This is because the motion of the atmospheric air and the changing air density and the temperature. So there is a change in the temperature, there is a change in the air density, and all this plays a important role for the apparent position of the stars and the twinkling of these stars. Okay? Yes, pay attention.
Because of this, the refractive index of air keeps changing continuously.
Can you see this changing?
Because of
Yes,
this
see
change,
apparent
the
position.
position and brightness of the star keep changing continuously,
And the star appears to be blinking, to be twinkling.
We do not see twinkling of planets. This is because planets are much closer to us as compared to stars. They, therefore, do not appear as point sources, but appear as a collection of point sources. Because of changes in atmospheric refractive index, the position as well as the brightness of individual point source change, but the average position and total average brightness remains unchanged, and planets do not twinkle.
And
By
therefore, this is the
sunrise,
reason
we
that
mean the
planets do
appearance
not twinkle.
of the sun above the horizon. But when the sun is somewhat below the horizon, its light rays are able to reach us along a curved path due to their refraction through Earth's atmosphere. Thus, we see the sun even before it emerges above the horizon.
Yes, this is the
Same
reason.
thing happens at the time of sunset, and we keep seeing the sun for a short while even after it goes below the horizon.
Okay, so see, as you can see this here.
Dispersion of light. Hold the
Yes, as you can
The
see here, see
apparent
please.
position of the star keeps changing a bit.
See, pay attention here. Talking about the sun, that even if the sun emerges below the horizon, we can see it above because there is an illusion kind of thing created. See, sun is
Earth's
somewhere
atmosphere.
below the horizon. So if the sun is below the horizon, the light rays are able to reach us through this curved part. See, as you can see this, the light rays are reaching there. It is going under the refraction, and it is changing, and it is bending, and finally it reaches the eye of the human being. So it appears, the sun appears to be still there even before the sunrise, and the same thing happens, exactly the same thing happens when it is a sunset.
Thus,
Okay.
we see the sun even before it emerges above the
Above the
horizon.
horizon. So even if it has not came above the horizon. Horizon is the straight line. Okay. So even before the horizon, we can see the sun because of this refraction taking place to different mediums and to a different denser mediums. Okay. Same thing happened in the
Same
sunset.
thing happens at the time of sunset, and we keep seeing the sun for a short while even after it goes below the horizon.
Okay, now let's move on towards the dispersion of
Dispersion.
light. Now, as I have asked you, what is dispersion of light? So, can anybody tell me what is the meaning of the word dispersion? Yes, can anybody tell me what is the meaning of the word dispersion? Yes, I'm waiting for your answers. Very good, very good. Yes, I'm waiting for your answer. Correct, 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 Tanishka. You're totally correct. Light gets refracted. See, Anjali, you have written as reflected. Is it reflected or refracted? See, tell me. Yes.
Dispersion of
Okay.
light.
Now pay attention.
Hold the plastic scale in your compass in front of your eyes and see through it while turning it slowly. You will see light rays divided into different colors.
Yes, see, this is a common activity which all one of us do, right? We hold a scale and we peep and we try to peep through the scale, and we can see that a normal ray of light it gets divided into a different colors. Like it appears to be light of a rainbow. So what exactly it is? Yes. So what exactly it is? Let's see. I'm
These
sure that
colors
everybody has
appear
done.
in the following order:
violet,
indigo,
blue,
green,
yellow, orange,
orange,
and
and
red.
red.
So basically,
You know,
you should know the formation and the proper sequence of these
and red.
colors. Fine. So it
You
is
know,
that for the colors, it is like violet, indigo, blue, green, yellow, and then orange, and then red. So it is also called as Vibgyor because you should know the exact sequence. So it is also called as Vibgyor. Such kind of things can be asked in your exams also. Okay.
you know that light is electromagnetic radiation. Wavelength is an important property of radiation. The wavelength of radiation to which our eyes are sensitive is between 400
400 to
and 700
700
nanometer.
nanometer. So there is a particular wavelength of the radiation to which our eyes are sensitive. There is a wavelength, there's a proper band where to which our eyes are sensitive, and the ratio and the limit is between 400 nanometer to 700 nanometer. All the radiations between this wavelength, between this 400 nanometer to 700 nanometer, we can see everything in between 400 to 700 nanometer. Okay, so now pay attention. This is
In
important.
this interval, radiation of different wavelengths appears to have different colors mentioned above.
So this radiation from 400 to 700 nanometer, we can see this all different kinds of colors. Okay.
The red light has maximum wavelength, that is close to 700 nanometer, while violet light has the smallest wavelength, close to 400 nanometer.
Yes. So the maximum wavelength, see 400 nanometer till 700 nanometer, all the colors can be seen. So this is the wavelength. So between 400 to 700. So the minimum 400 is the violet, and the maximum 700 is the red color. So the wavelength of red color is 700 and the wavelength of the violet color is 400 nanometer.
Remember that 1 nanometer is equal to 10 raised to minus 9 meters.
Yes, this nano, see, as we know M, if it stands for M, you have some different conversion. So similarly, for nano, it is 10 raised to minus 9, which also means 1 upon 10 times 0, like 1, 0, 0, 0, you have to write it 9 times. Okay? Yes, Mansi, you're correct. Vibgyor is the easiest way and the simplest way to keep this all things in mind. Very good, beta. Yes, you're correct. Vibgyor. Okay, so see, as I've said you, the maximum is the red color. So that is the reason why many of the danger things we have red color, because that color has the maximum wavelength and that colors attracts, and our eyes are very sensitive to this red color, as this we can attract it very fast. So red color has the maximum wavelength and violet color has the minimum, that is 400, and the red color is having 700. Okay, and this N here, N stands for 10 raised to minus 9.
In vacuum, the velocity of light rays of all frequencies is the same. But the velocity of light in a medium depends on the frequency of light, and thus different colors travel with different velocity.
Yes, so different colors travel with different velocity, but the velocity of light in the medium depends upon the frequency of the light. See, can you
Therefore,
see here?
the refractive index of a medium is different for different colors.
Can you see the refractive index of the different color? It is different. For red, as it is maximum, it is above. As violet is the minimum, it is somewhere below. So all are having a different refractive index.
Thus, even when white light enters a single medium like glass, the angles of refraction are different for different colors.
See, if you consider this single white light or this ray of light, see, this is going somewhere in a different way, and if you try to measure the angle of the refraction, you will find a different angle each time you go on finding a different color. Okay, thus even when the white light enters a medium like glass, and the angle of refraction are different for different colors.
So, when the white light coming from the sun through air enters any refracting medium, it emerges as a spectrum of 7 colors. The process of separation of light into its component colors while passing through a medium is called the dispersion of light.
Yes. So when a single white light enters into a spectrum, that enters into a glass, it further divides, it further spreads, it further disperses into 7 color. It is called as a dispersion of light. I again repeat, when a single ray of light enters into a spectrum, see, can you see this white light, a single ray of light? Yes, the single ray of light, when it enters from one medium to other medium, when it is entering a spectrum, what happens is this light is separated, this light is dispersed, it is separated into 7 different colors. See, it is separated, it is dispersed into 7 different colors. Now see what happens. Now the light is moving from one medium to the other medium. Okay, from one medium to the other medium. So here refraction took place. Here which process took place? Refraction took place as the light is going from one medium to other medium. Now coming here, this is further spread, this further spread, and in spite of moving from this medium to this medium, it is reflected, it is bounced back. Can you see the bouncing back of all the 7 colors? Yes, all 7 colors are bouncing back into the droplet only. See, they are bouncing back, and from here, so first refraction took place, here reflection took place, and finally again they are not reflecting, rather here they are refracting, from the droplet to the end. So here they are again refracting, all the 7 colors are refracting, and thus a rainbow can be formed. Is it clear to everyone? So this is called as the dispersion of light. This is called as the dispersion of the light. Again I repeat, see this white light from one medium, it is moving on to the other transparent medium, water, and here refraction took place. So as refraction took place, this white light is being dispersed into 12 things. See, this white light is dispersed into 12 different colors. It is separated into 12 different colors. It is passing and passing and passing and passing. And now, in spite of moving on further, again from water to air, it is not refracting. Rather, it is reflecting. So, when it is reflecting, it is moving again to the opposite end. And now, here it is refracting. It is moving from the one transparent medium, water, to the other transparent medium, that is air. So see here, you can see the dispersed form of the light. So this is called as the dispersion of light. I hope everything is clear to you all. If you have any doubt, you can ask me in the chat box. Yes. Likewise, we can see the spectrum to make the thing
Sir
more
Isaac
understand.
Newton was the first person to use a glass prism to obtain sun's spectrum. When white light is incident on the prism, different colors bend through different angles.
Yes, different
Among the
colors are
7
bending.
colors, red bends the least, while violet bends the most.
Now we know the reason
Thus,
behind
as
this.
shown in
Yes,
figure,
we know the reason behind this. Why red is the least and why yellow is the maximum? Because red is having the maximum wavelength and violet is having the minimum. Maximum of 700 nanometer and violet 400 nanometer. So this has been spread into the 7 colors, which is also called as Vibgyor, Vibgyor. Each stands for different color names. Okay.
the 7 colors emerge along different paths and get separated, and we get a spectrum of 7 colors.
And see, basically you can see the spectrum of the 7 color. Okay, so this is how we will end our today's lecture. Fine. See you all students in the next lecture. Bye everyone.